Okay, next question. It's going to be compute the Levenstein distance. I'm going to take a second to read this question because I actually haven't read it. So spell checkers makes a suggestions for misspelled words. Given a misspelled string, a spell checker should return words in the dictionary which are close to the misspelled string. Distance between two words as number of edits it should take to transform the misspelled word into a correct word, where a single edit is the insertion, deletion, or substitution of a single character. Okay, so we know that. I'm going to write that down. So minimum of the distance when given two strings. Okay, number of edits needed to transform first string into the second string. Two A's, that's going to do, and then substitute D with F, that's one, insert F, that's one. Okay, so answer should be 4 if we were to transform string 1 to string 2 in this particular example. Just making sure that's correct. Okay, do that. Okay, that sounds good. Now I've done something similar like this. 2, 3, 7 over here because a substitution is allowed. Okay, that idea is banned. Or we can insert B before A. I'm gonna use pointers be I1 for S1, I2 for S2. Now in this case, because the question S1 character, yeah. Next iteration, let's see if these are the base cases. I mean, sorry, these are the actual logic. Now, base case would be in order to match S2, we need match S2. So say we are at A, okay, if we move forward, if say I1 is first equal to what we need to do, like of S2, we need to do it. Okay, sounds good. Okay, sounds good. Now at this point, we either can insert back up here. But I'm not going. So I'm not going to do it. So that should insert, delete, and sum. So because this is going to do an extra step, we know these are going to plus 1, so these are going to, this answer is not going to be chosen because these two are 1 less than that. So, okay, so I2 is at the end of etching. We move next. One is at the end. And one is also, and so delete. It seems like the minimum answer is going to be 2 over here. And if we look back up here, it does seem like the minimum edits would be just at the end, return 0. Okay, this seems good. We can memorize by the current minimum. And j minus 1. So every time we go, I assume we will need to add 1 on both. So we reach the end of it. It's actually okay. Let's see if this works actually. I'm going to use the same example we had earlier. I'm actually going to be moving something. Okay, yeah. I think that is, so I is going to represent that's what we have up here.
Oh, I'm muted. Oh my god. Sorry. Oh my freaking god. I totally did not. I've been talking this entire time? Okay. You know, I will recap all my notes about this after this client. Oh my freaking god. I only just looked at the chat right now. I have my notes here, guys, and I'll go back over this video. Don't worry, stick around. I'll go back over my notes. And I'll show it. I'll show you. All right. But let me bring my other client on first, and let's look at his replay first.
Recording in progress.
I'm a great mime. Oh god, I am such a fuck up. Fuck me. Yo, what up?
Hey, what's up, Edbert?
Hey, I've been streaming for 15 minutes, and then everyone told me my mic was muted.
You're what?
My mic was muted the 15 minutes I was streaming before this.
Really?
All right. How's practice been for you though?
It's been all right. I mean, I will say just EPI is just like very the people who wrote this book definitely are like just very big brain, man. Like I think.
Yeah. That's why I said like EPI is like very good at making sure you actually understand what the hell you're doing.
Yeah, like sometimes I kind of like look at their optimal solution and I'm just like, fuck, like I get it, but like goddamn, like it's just like they wrote it in such a concise way, and whatnot. But yeah, no, it's definitely been like very for lack of a better term, like kind of like grueling, I guess, because I think with grokking the problems were just like significantly easier.
Yep.
Because it's like you know the pattern and whatnot, but for this one it's not necessarily like a pattern. It's just like, yo dude, here's just basically like a topic and whatnot. So yeah.
Let me actually look at your sheet. I think I had you do some EPI before, but I think now you've been geared more towards EPI, if I remember correctly.
Yeah.
Let me look at this. So I said that you had to do recursion, array, redo a lot of the DFS stuff. I think most of your DFS practice had been towards grokking, but you didn't really do much EPI.
Yeah. So there was just that. Let me look at study plan real quick.
Yeah, I'm looking at your study
no, it was essentially like basically we established that redo the DFS stuff I failed, and also like do every single problem within I think it was like in EPI, I guess, basically.
Yep.
So that's basically what I've been doing the past 2 days. Yeah.
Great. Yeah, because from the moment you said that, oh god, when you were talking, I'm just like, the past 2 weeks we didn't really make as much progress, and I think the reason why is I didn't have you focus as much on EPI because I was trying to fix your mechanical mistakes. So I think, okay, so now, do you feel like your logic and problem solving have been much better?
I would say so. Yeah. I mean, I think like in terms of like just the input and output kind of stuff, like when it comes to like establish the recursion, I think like it's pretty much there. Like, the mechanics and whatnot.
Good.
For like DFS and whatnot. But in terms of EPI, like, man, dude, like some of these problems, I'm just like, holy fuck, like, yeah. But yeah, I'd say so. I mean, I think just right when I'm thinking I like understand something, like especially with like binary trees, I'm just like, oh damn, this is totally new. But yeah, I say.
Yeah. The bottom line is being able to be very good at this logic and deductive reasoning. And that's what I'm trying to really stress into you. And all these different things I talk about, like writing out your idea, run through it.
Oh yeah. So yeah, I think definitely on that in terms of writing out the ideas and whatnot, I think I've definitely like put much more of an effort in. Yeah. So yeah.
Great. If you have the replay, send it to me so we can go over it.
Sure. Yeah.
Okay.
I'll send you the one I just did actually.
Why not? Yeah. All right, and now I'm gonna look at your practice diary a little bit right now. We had our last session 11:2, so I'm gonna start from 11:1. Okay. Recover binary search tree. Got the idea within 15 minutes. However, implementation of final code was incorrect. I'm curious why.
Oh, let me give you access.
Yeah, I'm gonna. Oh, I think I have access to this actually. Cool, sweet. So let's actually see here. You were given the root of a binary search tree where the values of exactly 2 nodes of the tree were swapped by mistake. Okay, so you have the correct. You say you have the correct algorithm. Yeah, but you said the output of the code was wrong. What was the mismatch here?
I just think my final implementation in terms of the right here, the recover tree part was wrong, I believe. I think this might have been a leak code problem. So
it's hard for me to say because I don't know what the leak code solution to this one is off the top of my head. But let me see. Traverse in order to once come out of order node, locate the previous node and swap them out. I mean, if you're guaranteed one swap, I think that's correct. So
yeah.
Let me see. Let me try to think of like a counterexample to. So this is just a combination of validating a binary search tree and yeah, it's a combination of validating a binary search tree and then some other component here, I think. So like whatever here, like you have the root sets the limit for left side, right side. And once you find a node that violates that, you have to find a node to switch it with. That's the other question. Well, the thing is that swap the value with the current node. That's the issue here because that's I think where your code is wrong. If you try to submit this leak code, I'm gonna bet like 80% is it's not gonna work. Because I don't know how did you determine what the node you switched it with and why was it quote unquote the current node?
Yeah, so I think like, the idea is like when you do it in order, right? Like you'll know essentially if something's out of order, if whatever node you're on, right, is like let's say less than what the previous node was before. Or something like that, right? Because in order is like for a binary search tree is going to be in non-ascending. I believe just essentially once you encounter a node in which it like conflicts with the previous node, then you can just like, if you already you have access to that essentially, like based off the in order traversal. So all you have to do is just swap the value with whatever the temporary value was that was set with the previous one.
I think that the better way to describe this is actually think of it like a wall. Where as you go down left, right, you're shrinking the walls, right? So like, for instance, if I'm going down, like, let's say this example number 2, right? In the proper binary search tree, I know that I need to go, if I'm on the right side of 2, then the minimum I can ever be is like 2.0001, you know what I mean? Like it has to be greater than 2. And then if I go down the right side from 4, then the most I can ever be is 4, right? So that's what validates it. So in other words, if you look at the original incorrect one, you see that 2 violates the wall of 3, right? Because when we go down the right side of 3, we know that we can never be less than 3. And as you keep traversing down this binary search tree, your walls of what is minimum and maximum actually get smaller and smaller, right? And so whichever wall gets violated is the one you get switched with. I think that's the way to do this. So I would have liked you to be much more concise with your explanation.
Okay.
Yeah, this is like that was like how I thought about it. So I'm pretty sure that your solution is not necessarily correct for that reason.
Okay.
Yeah. So I would say figure out like how to, like you saw how I was able to do it. I want you to actually try and figure that out, like why this may or may not be the case and how you could actually figure that out.
I'm
not sure if I'm right, but I think that's the way to do it. And
I definitely know that's like what you're describing is like the validation of the BST low key, right?
Correct.
Like, and like, I think with me, whenever it comes to those type of problems, like I like to take whatchamacallit, I don't know. It's like, I know that's like the correct way to do it, but sometimes I'm just kind of like, I think this way can work too. But yeah, no, definitely. I'll try to do it that way.
Yeah. I don't even, actually, now that I think about it, I don't even think my answer is even correct. I think it's the first node that gets, once you figure out that wall node, then you have to traverse back up to figure out if there are any other nodes that violated it before. For instance, let's say that let's say this was like 5 and 2, right? And then there may be a a 6 or 4 before that. Then maybe that 4 gets swapped. I would have to really test it, but this is like instantly what I'm thinking of when I'm just like looking at this at a cursory level. So and the only reason I'm thinking this is because I'm relating to a previous problem that I've seen. And then trying to modify it in order to fit this new problem. So I think that's kind of like your idea needs to be a little bit more complete.
Okay.
Did you? And
my idea was just kind of thinking like, what was it? Because they're talking about like the Dude, why did I think about in order, actually? I'm curious. Because I saw BST, and I know, like, in order, like, has to give it in, like, non-ascending order. Like, it's going to be sorted. And kind of just based off the example, I was like, okay, if it's going to be whatever it's going to, the way it's going to be sorted, essentially, I think in the context of the problem, the node, there would only be, like, 2 nodes or something like that, so...
Yeah. So this is you like being super obsessed with like being with the traversal. That's it. I need you to let go of that. Like not there's multiple ways of handling tree problems. And you are so hung up on traversals. I really need you to like let go of the traversal.
Okay.
And solve the problem holistically. I really want you to do this because I think you're still hung up on grokking, and I need you to like think more in EPI of like growing your solution. So I'm gonna make a note of that. Less grokking, more EPI. Because I think up to this point you've been mostly trying to figure out the mechanics of the problems, but now we need to focus on your problem solving. So this is where this is gonna kick in. So let's go to the next problem. Got the stumble bit when testing. Other improvements are fast and erratic. If you felt you did good on that, that's fine. Optimal solution, only EPIs returns an object consistent of int and a node. Overall, glad to remember the idea. Okay, looks like you did well on this one. I want to see this one.
Yeah, for sure. Let me
let me actually share my screen.
share this one. Oh, this is the lowest common ancestor one, which we've done a couple of times already, but I'll share it with you still though. So
here, just give me the access.
I'm gonna send to Edbert. Got you. I should share right now.
Okay, let's see.
Yeah, this one I really wrote down the ideas, I think, so.
Yeah, you better, because we did it a few times. I'm gonna be mad if you didn't.
Yeah, fair enough, man.
Okay. So let me request the thing again.
It should be, you should be added, yeah.
Cool, got it. Yeah. Yeah, you ran through it. Cool, perfect. You did the mechanics of it. I'm perfectly fine with it. Let me ask you, what do you feel like how you could have gotten this faster? Let me ask you that. What did you spend the most time on? And what do you feel like you spent the most time on that could have been a lot better?
Yeah, let me look at the notes really fast. I think again, I think it comes down to when I write down my ideas.
Okay.
Like sometimes it can be like I actually don't know where I could have spent less time on. Actually, I felt like all of this was like kind of necessary simply because like I had to like think about those 2 cases, right? And I had to like do like some form of testing and whatnot. And I guess perhaps like my testing, like if I'm doing like a tree problem, right? Like, and maybe I could have done like less testing. Maybe it's like once I kind of like know, like, for example, I don't have to go all the way to the leaf, perhaps. Like, I know that's going to be returning either none or like 0 or like whatever the case might be. Like, I don't have to go all the way to the leaves and stuff like that. Maybe that could have like sped it up faster.
Yeah.
But other than that, I feel like everything I like wrote here was like necessary because like specifically this part right here, it's like, I find that like when I do like tree problems, a lot of times it's R actually told me this, but he was like, yeah, just think about what you want to be doing at each one of these nodes and like what could be the possible cases. And since I've done this problem before, I kind of was just rerunning through that. But like in all honesty, I kind of just came up with this still like just by thinking about the conditions and whatnot. So
that's fine. I think everything you've written here is pretty reasonable. The testing, like you said, once you have like run through the tree, you don't really need to run through the whole tree. Like there's like for instance, if I put like a test, like if I asked you for like how to say the common ancestor of 1 and 6, it's not really any different than me asking of like on the right hand side. It's not different than me asking you the ancestor of 6 and 0.
Yeah,
it's fundamentally not that different. As long as I can handle the traversal, then I can just put it on one side and get to it faster. There's no point in me running through the entire tree just to test one case. When I could just do it earlier. So there is like what I said about states before. I think I told you this before. Like testing via states. As long as you like handle the states that you can run into and handle all possible cases, then you're gonna be fine. And like you said, that R told you that it should be about what you want to do at each step. So that's the key thing here. So I'm glad he told you that. Other than that, I think your Sudoku's slightly verbose, but I'm not gonna harp too much on it because I'm happy that you actually got the answer within 30 minutes. So that's good. That'll keep the idea a little bit simpler, but I'm not gonna pick on it. I think it's fun.
Yeah. Got you.
Right.
And then there's I think.
Okay, you said ask my opinion on the sum to leave.
Yeah, actually that one.
Requesting access. Okay. And then the last one, since you didn't write anything, I won't grade it. We'll just go to the replay after this one.
Oh, the for the compute the kth node?
There's like 3 of them. Lines 30, 31, 32.
30, 31. Yeah, 30 I was just kind of I don't think that was one that like was even worthy of replaying just because I couldn't get the idea, and I think that was just like I just need to study that.
Okay.
Like how to do it.
Well, not just study how to do it. It's also like understanding where you left off, where the book is, and then like differing the two. Like how could you have gone from where you went to where the book is? You know what I mean?
Yeah, I think just fundamentally speaking, like it was because the whole concept of like traversing a tree, it's because I think I was practicing with mechanics of recursion so long, I didn't know how to implement it like without recursion.
Okay.
So it was like around like 15 minutes, I was still struggling to come up with the idea. I just kind of called it.
Okay.
Which is why, yeah. And then some to route to leaf path. I think we've done this problem once before, but like I don't remember, so that's why I kind of was like, oh, ask you about your opinion. So
that's fine. Wait, I'm requesting access again.
Okay.
Yeah. For the problem that you don't remember, I think that's a good thing, because then like you can really tell if you actually understand, like, because a lot of these problems that we do, I tell you very specifically what your mistake is, and if you can see that you've made progress on it and you're not hung up on the same spot, then you're doing something right, and it's okay to like make another mistake on that same problem,
Gotcha.
So don't worry if you like. I think it's better if you don't remember how to solve it.
Yeah, like LCA, I never remember actually how to solve.
Great.
Yeah. And then for this one, I guess like two things, right? It's like one, I'm kind of just unfamiliar with like binary stuff, but I don't think that's like the actual issue of the problem. I think just I was confused as to like if the book solution and what I'm doing, if my solution is like at least somewhat optimal compared to the book solution.
Are you talking about the route to leaf paths?
Yeah, route to leaf paths in a binary tree.
Okay, so let's see. Traverse DFS design algorithm compute the sum of binary numbers represented by. Oh, this is binary numbers. Okay, we never actually did this problem.
Okay.
That's fine. Okay, so then you could traverse binary digit, add that binary digit to global sum. Whoa. At each node, append that string to the digit. So you're building up the binary notation of it. Oh, okay.
Yeah. And what the book was doing, let me pull up.
I know what you're doing, and I know what I'm gonna guess that the book was actually saying, hey, if there is a 1, then multiply by 2. Wait, no. Do it by 1. Multiply the number that they already have by 2, and then add this digit. If it's a 1 or a 0. Is that basically what it's doing?
Yeah, low key, I think. It was was that we take the integer for the node's parents, double it, and add the bit.
Yep.
At that node, yeah.
Yeah.
And I guess I was just a little confused about that. Because like I'm kind of reading it and it seems to be doing like a calculating something called like the partial path sum.
Uh-huh.
And then they if it's the root, then they return that like partial path sum. Whereas like I guess for me it's like if the node is a leaf, then I just like I convert it into a binary number, then I just add it to the global sum. Like I guess the mechanics.
Yeah, so the reason why is because it's cheaper to store an integer than it is to store an array of strings. That's pretty much it. So that like for instance, the binary number that you can run into can have like 32 digits, and so you're gonna have a lot of strings that you're keeping track of. Each string is gonna be what, 16 bytes? Or yeah, it's like a byte. Yeah. So one character is a byte. So then you're gonna basically carry around 16 bytes, but instead of like a byte for every single binary representation, right? But then if I'm doing an integer, then I can just use 1 byte to represent that as well, no matter how long it is, assuming that the tree is of like 32, right? So basically, you're just using more memory than necessary, and it's kind of important to think about that.
Okay, so what they're doing is like they're like just straight up converting it into like an integer or like using integer actually.
Yeah. So basically,
okay.
as they read it, they
Okay.
just add that to the running sum, and then when they get to the next bit, they bump up the value of that sum by multiplying by 2, and then add that next bit in to represent represent that. So for instance, let's look at this number 1000, right? So then this 1 would represent, at this point, would be, once we read it, it's going to be a 1, right? And then we see there's another bit available to us. And so we're going to multiply by 2. So now 10 represents 2, right? And then we see another 0. We multiply whatever we have by 2, so that's going to get us 4. So then 100 represents 4. And then you kind of see how they're doing it.
Yeah.
So they just like store the number that they already have and then multiply it up, and they're reading it from left to right. That's it. So they're doing something substantially different than yours. And the insights in order to do this was really, how can I store use less memory, which involves understanding how many bits and bytes certain variables use or certain data types use. And the second one is, how can I do a lot of this computation while traversing?
Okay. Yeah. I think that leap in logic isn't too far away from me. I think I was just kind of like, yeah, that's fair. That's fair, actually.
Yeah, see, a lot of these things is just usually just one or two simple observations that you could have probably thought of, and all it really boils down to is how can we make this more optimal?
Okay. But yeah, I think yeah, I was just reading that and I was like, huh? Like, yeah, I if this was just like a regular number, I think I would have gone with that, like keeping the running sum. Which is what I guess I was trying to do with like global plus equals to.
Right.
But their solution, I think, makes more sense. Okay.
Yeah, it's a lot more mathy and less confusing because you have a lot of these like bin. I've never heard of this bin function in Java actually.
Oh yeah, no, this is like a Python. It's like the idea was like convert the binary string into. I wasn't too obsessed with like calculating it because I knew like, or at least I thought that wasn't important, but it turns out to be important actually. So
yeah, that's fine. All right.
But,
okay. Okay, go
ahead. Yeah. So this one, let's see. I guess the problem I did kind of want to talk about was compute or I guess I'm not sure which problem to kind of go over to do the replay. Because for one of them, it's the implement in order traversal one. I just didn't know how to do. For the other one, the kth node in an in order traversal, I kind of got the correct solution. And I have like a more solid replay of that if you want to go over that.
Whichever one you feel like you are going to learn the most from.
Okay. Since I have more information on the compute the kth node in an order traversal, let's do that one.
Okay. So
and yeah.
To me.
And let me share this with you. The recording. Do you need the recording?
Yeah.
Okay. All right.
Cool. Let's see this. Personal meeting. Cool. So let's see what you got here. Write a program that computes the kth node appearing in an in-order traversal. Okay. I think this one's pretty easy. This one should be pretty easy.
Fuck. All right.
Wait, what's the fuck?
No, I didn't think it was like easy, but
right.
Yeah.
Let's see what you do here. Okay, we're jumping to when you start. So you spent basically 5 minutes being quiet. So okay.
Yeah, I was just thinking. I was like, because I knew it was like if the book says like, all right, dude, it's like pretty trivial to solve this no then. And I was like, I that into an array.
Okay, you're storing an array, and then just get the element at the index.
Advocate the position.
Yep. So okay, honestly, that should have been the first thing that I should have gone on the paper, and I feel like you could have done that very quickly. Was this just an idea you're holding in your head, or what
yeah, holding in my head. Like I knew it was going to be like that, right? But I think I was just immediately like thinking about how I can improve on that. Just. I know I shouldn't be keeping it in my head, but honestly, like the jump in how to do it optimally was like just not clicking for me. So I was like just kind of stuck on that.
Yeah, but still, if the idea is in your head, put it out on paper. That way you can think about other things. That way you're not busy remembering it.
Okay. Fair enough.
Yeah. So don't like. We still don't keep the ideas in your head. That's what we're trying to focus on here. So.
Okay.
That's the first thing. Stop a traversal. Yeah. Yeah. So this should have been like. Okay. So yeah, you figured out you should keep a counter and stop a traversal when the counter reaches K. I think the question that you should have asked yourself after putting the naive solution is how to improve the efficiency. So, how to improve the efficiency? Don't use as much memory. How do you not use as much memory? Don't keep an array.
Right.
So let's see. Okay, here. So when the counter reaches K. All right. So then, I'm looking at this, trying to figure out what is taking so long, because I feel like this idea should have been out in like 4 or 5 minutes. Why is it like 8, 9 right now?
Dude, honestly, I think I was just like thinking, man, like I couldn't think about like, because I was like, okay, we're not going to keep track of it in an array. That's pretty obvious. But stopping it, like the traversal when the counter reaches K, like how, like what if, like in the worst case solution, right? The K is on the right side, right?
Right.
And whatnot. It would still take O of n time, and I think because the problem was like, okay, trying to solve this in O of n time complexity, each node stores the nodes in the subtree rooted at that node. I was like, okay, how can I use that information to help?
Okay.
And whatnot. So yeah.
But the thing is that you've already stated that you can improve this by keeping a counter and stopping the traversal when the counter reaches K. So.
Right, but I think I immediately just thought about like, but I'm not really using the assume that each node stores the number of nodes in the subtree rooted at that node. Like I felt like that information was like critical. So
what do you mean? Well, oh, I see. You got sidetracked.
Yeah.
Yeah, this is basically, how do I describe this? You are expecting things to be handed to you on a silver platter because it's like, oh, well, what if I know all the elements that are below it, you know? But it's like, you could figure that out yourself with the inner traversal. Do you have the question is really, would it not you have the tools to do it? And you actually do. So to me, it's like, if you have the tools, like, why not just use it? You know what I mean? Like, it's hard for me to describe this because it comes from a, like, it's not necessarily your fault. Like, you might have done too much grokking and you're, like, slowly weaning it off. But basically, the bottom line should be thinking about, hey, do I have the ideas and tools necessary to solve this problem? Like, I mean, it's okay to just, like, expect, hey, oh, I don't have this. Then it's like, okay, move on from that. Like, if you don't have it, you don't have it, you know? Don't get hung up on it.
Okay. So I should have just like started with the naive solution and just been like, fuck it, like let's just do it like here and try to iterate, right?
I mean, you don't have to write the naive solution, but you already had it. So, again, like like you said, you're like expecting that the problem would have given you the number of elements below a particular node. But the thing is that, well, you don't have that right out of the box. So if that's something that you need, why not just, you know, get it? Or, you know, in a better case for me, the way I would see this is if I'm doing an inward traversal and then when the counter reaches and stopping when the counter reaches K, I'm just gonna do it because, you know,
no. I meant the problem stated that each node has like the number of nodes in the subtree root at that node.
Oh.
Yeah, so it was handed to me, but I was just trying to think about how to use that information essentially.
Okay, I see you. Okay, I mean.
Yeah.
Okay, now that I see that it was stating the problem, okay, that I understand where you might have gotten sidetracked. I don't think it's unfair for you, Shuby. I would have, yeah, but you're right. I would have gone to immediately the naive solution because that's order n. But is I trying to solve this in the less than order n?
Yeah, that was all provided in the context of the problem. They're like, oh, try to solve this in less than O of n time complexity, and I was just like, oh fuck,
I see where you might have gotten fucked up. Okay, that's my fault for not like seeing that part of the problem. All right, so then let's think about this. Like going from this solution, like our counter when the counter reaches K, and then assume that the node stores the number of nodes in the subtree rooted at that node. Then how does this help? How does this help you actually? I'm curious. Like can you use that information?
Yeah. So like I like just sat with that like little like for a long time, and then I was just like, I had to like draw out an in-order traversal and think about it. I think. But I just assumed that if you know like if you know the number of I think the thing that eventually clicked for me was just like If it's less than O of n, then like, we're probably going to be like subtracting away a huge amount of like the tree, right?
Sure. Yes.
Like a non-trivial amount of the tree. And if we know the number of nodes, then it's just like, that means like we can like how can we discount like part of the tree? And the idea that eventually just came out, just like, we would skip it because like if in order it's left subtree, then the node, and then right subtree, then we would skip the left subtree if it is if it's basically like, I think less than k, right?
Yeah.
Because then we know k can't exist in the left subtree. Like say for example, the left subtree only contained like 3 nodes and we're trying to find like the 5th node. Then like it would have to be on the right side of the subtree. So yeah.
Right, exactly. Because the whole reason you're counting up k is to, basically say, hey, I've already checked all the nodes in this subtree. But if you already have a piece of information, like the number of nodes stored at that node, the number of nodes stored at that in the subtree of that node, then you don't have to do the k number of operations in that subtree. So you see like how that logic kind of falls out?
Yeah. It took a long time though to get there, low key. Like I had to like, but I do see where that logic kind of came out. Like I think you're describing a sense of like, how to improve efficiency, right?
Yeah, exactly.
Yeah.
So that's really like the only difference. I didn't have to draw it out. That's the only thing. Like I just like I came from it like purely from a high level standpoint. Like, oh, this is how we do it just off of efficiency. So I mean, yeah, I get like testing it just if you don't see it, but the question then becomes, how do you get to a point where you can see it without having to do that?
I think a good idea would just be, I think I'm on that path, but I think you described it brilliantly where it's just like, how can I improve this efficiency?
Exactly.
Like, yeah.
So, all right, that's fine. If that's the key to it, then we can, let's see, what else you do here. Okay, so we subtract k, traversal, switch. Okay, so you end up eventually figuring it out after 15 minutes. Okay, fine, fair.
Yeah.
Okay, so then what do you do after this? My question. Okay, so then I guess you're testing the idea. Fine. Yeah, I think that like on a certain level, if you know the idea logically falls from one to the next, then you don't need to be as like super rigorous with the testing. But in this case, I understand why you're testing, just because like you're not sure about the idea, you want to run through it, making sure you understand it. This should only take you like 5 minutes though.
I see. Yeah, I think now it's like I'm not necessarily paranoid, but like definitely testing takes a long time. I actually had a phone screen. They're like, you're pretty thorough with testing, and I'm just like, but no.
Yeah, was this Google?
No. This was just like one of the startups and whatnot. But yeah,
I mean,
I had a Audible what was the online assessment today? But yeah.
Okay. Yeah, I mean, testing, being thorough with testing is fine, but it's like there comes a point of diminishing returns. But if I had a choice between a candidate who didn't test and a candidate who overly tests, I'd rather pick the overly test. You know what I mean? So now all that's left is for us to really, like, you have the same problem as R does. So what we need to do now is to cut down the amount of testing that you're actually doing.
Yeah.
So it's fine. You can at least do this if the situation required it. That's the point. The next point now, we're going to optimize over it and say, hey, well, maybe we don't need to do as much testing as we think we need to do.
Yeah. Some of it, honestly, is just like the structure of like binary trees itself, you know? It's just kind of like...
And so if it's the structure of the binary tree, that means that you need more practice with the binary tree. That's really all it's saying here.
Oh, no, I meant like in the sense of like testing it, though. You know, you have to go left, you have to go right, and left might contain. But yeah.
Yeah, I'd be like more staccato. Okay, da. You know, you spend like 10 minutes testing it. I think you should cut this down to 5. And based on the way you're testing it, I'm guessing, yeah. So let me show you a trick here. So let's say I'm testing it. What are the states that I'm going to run into?
The node is either going to have both children, one child, or no children.
Sure. What else are we controlling for?
We're also controlling for like k.
Okay.
K is like 0 if it's 1, or like, you know. So yeah.
be more elaborate about K. What are the ways we can divide K into? What are the states?
The states we can divide K into, K is going to be it's either going to be like 0 or not 0.
Oh, you're decrementing K. I see. You're decrementing. Okay, fine. So it's gonna be either it's gonna be 0 or not 0. Correct. But let's be a little bit more specific. What I would have liked to say is if K pointed to the left subtree, the right subtree, or was the node itself. If it went 0. You know what I mean?
Oh, interesting.
Yeah. So let's say that if the K, let's say K was equal to 0. Well, the thing is, it's kind of weird because you set it up as a global variable. So then what happens if you, let's say like for the sake of argument, let's take this for example, right? So let's say
oh no, that I know that I wasn't trying to set K as a global variable. I think I just stated K.
Okay.
Equals to 5, yeah.
I think K as a global variable is okay, but it makes things a little bit more, like not as, a little bit complicated, but basically the point here is that, let's say K is not a global variable. Let's say that K is like 260, so it becomes the left subtree. And then let's say K is equal to 271 or 271. Then it would be 6, right? And then let's say it's greater than 271. Then it'd be in the right side subtree. Those are the 3 states I was really talking about.
Oh, wait, say that one more time, Edbert.
So the idea is that the K can either point to a node in the left subtree, can point to the node, or can point to the node in the right subtree.
Correct. Yeah.
So those are the other states that you need control for. So if you can come up with a test scenario, or at least like run through it enough, or create an isolated scenario where that is the case, then I think that's where then you'll be fine. That's where what you really need to test for. So instead of running through the entire tree, you just really need to test for I think essentially like 3 cases, just where the location of K, because whether or not there's a left subtree, right subtree, or is like whether or not there's a left subtree or a child or no child doesn't really make much of a difference. I don't think, or at least it's very trivial to test that.
Got you.
So it's like some of the stuff that you skip. Like for instance, what happens if we're at a node with one child, what if we're at a leaf node and K is super enormous, like 500, then it's obvious that there's no children to go into, we skip it. Like that. It's like that,
Okay.
That's like a super trivial thing that as long as you handle the null case, you're fine,
Gotcha.
And so it's also, you need to remember to decrement by 1 whenever you visit the node as well. So it's just small things like that. It's like really understanding like the small cases you need a test for, and then it's like solving it within like 10-15 seconds of what you need to do. That's how you get to the 5-minute mark.
Fuck, alright.
It's fine, but other than that, I'd rather you be more complete and thorough than to be sloppy and incomplete. But yeah, you can solve this in like 25 minutes. I think 20 if you really knew what you were doing.
I see. Got you.
Okay.
Yeah.
Yeah. So are you writing all this down? Like everything I talk about?
Okay. No, I did not write it down.
Okay, I'll write it down for you. But but in the future when I'm talking, I think you should probably write it down just for your own sake as well.
Okay, got you.
I know what is. I think I mentioned test by states with you, right?
Yeah, test by states.
Yeah, so just look at those notes again.
Okay. Got you.
Okay, and then also. Okay.
Yeah.
Anything else?
And yeah, something I kind of like wanted to touch upon actually is like I noticed in EPI, right? Because it's different from grokking, like oftentimes when they like solve a problem or whatnot, like they actually won't use recursion by like default. And I guess I'm just kind of curious, like, is there like kind of like preferred method or not? Because the optimal solution for this one, it's like, I would say the structure is kind of like the same. They just use like a while loop, and whatnot. Yeah, I was just kind of curious about that, to be honest.
I mean, either way is fine, but it's important that you're able to do both.
Okay.
So it's like there is no, I'm not gonna say one is more correct than the other, but I think that it's just easier to, I actually don't know why they would do that. So
yeah, because I'm like for this problem at least, right? for the compute the K node, they did something like wild tree, and then they computed the left subtree size. They do that comparison, and then depending on that, they switch the tree either to tree.right or tree.left and whatnot. Which obviously makes sense, but it's sometimes kind of just difficult to like switch between styles. So I was just kind of curious.
It's like you should be able to switch styles, though. That's the thing. Like you can do recursion, you can do iteration, doesn't matter. But it's like if I ask you to return a recursive function into an iterative one, you better be able to do it.
Not you.
Yeah. So other than that,
Okay.
it's gonna be fine.
Okay.
As long as you get like the spirit of the idea right, and you understand that you can convert when you convert your recursive idea into an iterative one, and you still get the same answer, it's fine.
Okay, got you. Yeah, that's something I try to work on, I guess. Let's see what else was in there. Yeah, but other than that, I'm trying to. Sometimes, like when it comes to the specific, because you can't really run the solution and stuff like that using EPI. Like sometimes the optimal solution versus like my solution like is a little off. Like, could you kind of like explain like how you would evaluate perhaps like when you write down your solution versus what's an EPI?
I would probably just do a run through of their algorithm, and just make sure that everything that I'm doing is pretty much what they're doing as well. I just probably run through a few basic tests like, okay, well, based on my understanding of what I need to test, let me run these test cases. That's really it. And then if like they look about the same, if the output and the stack trace looks about the same, especially if it's like recursive or not, then it's like, okay, then it's probably good enough.
Okay, got you. Yeah, because I was kind of just concerned about that. Like, obviously, like for this example, it's like some of the mistakes was just like the decrementing of K or like, you know, wherever the left subtree size is, and I feel like those are kind of minor, but I think yeah, sometimes I'll just look at their solution, I'll be like, yo, this is like so concise that I don't even understand it. But
it's like if you need to understand it though, because you want to get to a point where your solution is as concise as theirs.
Right, yeah, makes sense. Okay,
so
got you.
Yeah, and plus like the more concise your answer is, and like there's a whole lot of thought that goes into like and I'm sure you noticed this, that in order to get an answer that concise, you have to be that precise with your ideas as well.
Yeah, no, it's absolutely fucking crazy, man. Like the one of them is like find a root to leaf path with the specified sum, and I'm just reading this right now, and I'm like, this was like honestly 6 lines that they did, and yeah, it just blows my mind, like low key.
So the question is, how do you get to 6 lines?
Yeah, I guess just practice, man. You know,
pretty much, and then looking at like what they're doing versus what you're doing.
Yeah, just practice. But yeah, they mentioned a lot about like brute force, and yeah, like brute force it is just kind of crazy though, because sometimes you think about it and then you're just like, dang dude, like so much, like the way like I used to just write code is just like not necessarily trash, but it's just very
It's probably trash, let's be honest.
Okay, fair enough. But yeah, I'm just looking at this, I'm just like, yo dude, this is like gold standard right now. Like the shit they wrote. So yeah, but that's pretty much it. But yeah, no, honestly though, like working through EPI, it's like it's good. It's definitely like much tougher than grokking though, so that's why I didn't get through as much problems that I thought I was going to get. In comparison to grokking. But yeah, that was pretty much it. I mean, in terms of, I kind of wish I recorded more actually for some of the previous problems, so I can have you look over. But you can feel free to take a look at like the Google Docs too. If you want.
I think that I have a good idea of where you're at. I'm going to say that for EPI, I think let's keep a track on what we're doing. How close are you to being done with binary search trees?
For the binary search trees, so right now this is actually binary trees. This chapter.
Binary trees, yeah.
Yeah, so I would say I have. Let me count how many problems I have left. I have, I think 6 more problems. No, wait. 1, 2, 3, 4. Yeah, 6 more problems left.
Okay.
For binary trees. Yeah.
Okay, so you have binary trees, 6 more problems left. And you got through all the DFS stuff in grokking as well. I mean, not
yeah,
EPI.
Definitely.
You got through EPI?
The DFS stuff there's not actually a DFS chapter, right?
Okay. Let me double check.
Yeah, I don't think there's a DFS chapter in Grokking. I mean, in
EPI.
an EPI.
Okay. Yeah, you're right. It's just the binary tree stuff.
Yeah,
Okay.
binary tree.
Okay. So then.
Yeah.
Yeah. Go ahead. Yeah. Go ahead.
Yeah, I was planning to either finish a couple more problems from binary tree. Specifically implement an in-order traversal without recursion. I was going to redo that problem, and also the they have reconstruct a binary tree from traversal data.
Yep.
Like I was going to hit those two. The other ones, I'm not super sure on if I should do, but I guess I should.
Okay. Yeah, just do as many as you can. I think that is good practice for you. So if you have to do all of them, do all of them. And if you still find like this weekend you still have time, do the recursion chapter.
Okay.
Yes, let me add that. Oh yeah, so the recursion chapter. I think I sent it to you already. Did you do it before?
So I think we just kept focusing on like binary trees.
Okay.
And because the binary tree kind of stuff like involved the recursion, so we didn't really like target specifically recursion as a chapter. Instead, we kind of were just targeting like binary trees and binary search trees in terms of the problems we've done.
Okay. Yeah, so I want you to do the recursion chapter if you have time. And I think that once you get through a few of the recursion problems, I think you'll notice like a big difference in your problem solving ability. So, but make sure you really take the time to go through like what EPI is doing and what you're doing.
Okay, got you.
Okay.
Yeah, I'll do that. And yeah, I'll do the fuck. I can't okay, I'll do that. And then let's see. The other part for this weekend was the binary search tree one. Honestly, I'm just hoping that doesn't take too much time. Because I hope they're really similar to binary trees.
Let me look at your schedule. Given the pace you're working at,
yeah, these do take much more time than I like.
Yeah, that's fine.
Yeah.
Quality over quantity, man.
Yeah.
Yeah, so you basically have I would say probably around 20 to 25 hours this weekend.
Mm-hmm.
Yeah. I think you can knock out easily one chapter or two.
Okay. Yeah.
Yeah. But I mean, like, yeah, you're gonna have to like kind of give up a lot of your free time, but based on the schedule that we've set, we've already accounted for that. So.
Yeah.
Yeah. So really dig into like.
Out of curiosity, I was low-key thinking about hitting recursion chapter before the binary search tree chapter, just because I've been doing so much trees. Like I know like it might not seem I'm getting good like that good at them, but like I don't know, just like change of pace to do recursion first.
That's fine. Yeah, that's fine. I don't care.
Okay. Yeah, just in case like I like don't finish the binary search tree stuff, just wanted to make that. I know that, yeah. But,
that's fine. Yeah, so I'm looking at the schedule. Have you been keeping track with like our daily schedule for like studying?
Yeah, and yeah, no, definitely. Like I think yeah, no, I definitely have been. Yeah.
Okay. So no time or days missed so far?
No. And if it does happen, like I would say like for example, today I spent 2 to 3 more hours today just because like Wednesday I only did like 2 hours.
Okay.
Yeah.
Okay, so you move stuff around, but overall you keep with the schedule pretty well. Okay, fine.
Yeah, like net schedules basically. Yeah, I know that's not like the best sometimes, but it's just like sometimes if like I'm missing an hour on one day, then I make up for it the next day. So
okay. Yeah, but I try to keep with the schedule as strictly as possible. And if there's any dates that you miss or fall short on, let me know as soon as possible.
Yeah, for sure. But yeah.
All right. So then, looking ahead. Yeah, you can nail the recursion. We might be able to hit dynamic programming sooner than I thought, but yeah, array and linked list we're gonna need to handle next week. And hopefully with the emphasis on testing, we can actually start putting you for phone screens. But it all depends on like this weekend and how good you get at recursion.
Okay, gotcha. Yeah, how would you say right now, kind of like I'm doing on trees?
At least you're getting there. You are like you've done like what we're talking about. Now the question is, can we get you faster? So right now you're thorough, which is good. We need to optimize that now. And so I think as long as you like try to get as close as you can to the elements of programming interview solutions in terms of like conciseness and like being able to improve the speed of your thinking, we'll get there. And then the testing one, don't worry, we'll talk about that next week.
Okay, got you.
And then R, I talked to him about dynamic programming. Have him give you a spiel the week after.
Okay.
Before you go on
Sounds
vacation.
good.
So yeah.
Yeah.
All right. Anything else?
Nah. I'm trying to see in my notes if there's anything. Yeah, I think a lot of it is just one sometimes it's just like the idea part, but I think that part can just be, I want to say can just be solved by like, yo, just put down the naive solution, just think about why is it inefficient. Just do it like that. Like let me see where else is something that I need to got the idea within 15. Okay, implement. Yeah, if it's an implementation thing, I think sometimes that can be a lesser error just because like I'm assuming in an actual interview, like hopefully the interviewer will, yeah, but let me see. No, I guess nothing else. It's just honestly like getting through the problems, man. Like it comes down to it.
Yeah,
you know,
just put the time and quality effort in.
Yeah, quality effort. Yeah.
Right. But yeah, that's it for me.
Okay.
I guess I'll let you go early since there's nothing else.
Got you.
Right.
Okay. Right. Sounds good. Yeah. Yeah, let me just jot this down actually in the notes. Give me just okay, okay. So there we go. Fuck, what was this problem? Implement an in-order traversal without recursion. Do this one. And do recursion. EST finish binary tree chapter. Okay. Okay. Sounds about good.
All right. Cool.
All right.
See you later.
All right. See you.
All right. So that's that. Let's actually look at the so I'm gonna go back to what I was saying at the beginning of the stream about this particular replay, and I'll share with you guys. I'll talk through my notes again, since apparently I didn't turn on my goddamn mic. So let me open up the notes again. Okay, so this is the Levenshtein distance. Bottom line, this is like the string. This is the string. The difference between two strings and number of steps it takes to convert one string to another. So what I noticed here was that
between two words.
So what I noticed here is that I think he had trouble understanding it. So it's fine. He copied the problem down, and he's just like copying he's just copying the overall problem down. Fine. And then like for the first 3 minutes, he's like trying to run through a few tests and make sure he understands the idea. I'm actually okay with this. Like, like why is this answer the answer it is, and can I try to contrive it? So this is fine. But then I think one of the first things that I noticed when he's talking here,
let's see, 1, 2, 3,
is that he is
7,
using a long longest common substring pattern here. I think that's like, it's kind of a misuse, only because like for longest common substring, in general, you're talking about strings that are, relatively contiguous. And so it's not immediately clear if longest common substring here is going to work. I mean, I think it's fine that he tries the pattern, but I would not try to double down on it. The point here, I think, is to really think about the dimensions you're optimizing against. So let's actually see where he runs with this. And he goes here. So then he's back to testing again. But I think it's like a derivation off the longest common substring problem that he was thinking about before. So overall, this is fine. But I think it's a little too much testing. But either way. So again, so now he's like actually trying to figure out like what he needs to do. So he's figured out that, hey, I'm going to iterate through both my strings. And I'm gonna optimize against the insert, deletion, and substitution dimensions. So if I insert something, then I take the index -1 of one of the other strings. And then vice versa for the delete. So I'm going to compare like index I to index, j -1. And then for the delete, it's going to be the opposite way around. Index j and then I -1. And then add +1 to the operation in order to represent, hey, I'm actually adding a element in here. And then for the substitution, what you end up doing is you actually look at I -1, j -1, because the element at I and j here, I and j might actually not be equal, but the elements at I and j are going to be replaced. So that's one operation right there. So I think what he has here is correct. So if I look at this, I think it's correct. You know, the indexes, he's kind of going from backwards, from right to left, you know. And that's fine. But I would say that it's a little bit confusing to do it like that. I'd rather do it left to right, but it's whatever. And so I like when you notice here, he does I2 minus I1 in base case at the end of S1 and at the end of S2. In theory, when you do dynamic programming, you should not need to have things like these. And so what you're gonna notice here later on is that he actually tries running through the idea in order to test the base cases, but then he replaces it with length of n s minus 1 I minus 1 insertions. I think it's like, okay, fair, you know, but in theory, the code should be good enough that it doesn't actually need this. And so now like he's gonna go over this, and then he's gonna actually try testing the code again against this idea. So he's realizing he needs I minus 1, I2, and he's like walking step by step over and over through it. But one of the things that what you're gonna notice is that he's gonna add another observation in here and refine his idea. If I can find it again. Wait, where is it? I know I put a time span at 1546, I think. Yeah, this one. So this return minimum. Return minimum, I think he could have easily figured this one out beforehand. But the thing is that he needs to be very, very selective of when to use each one of these operations. So let me actually write that down. So the reason why this is kind of dangerous is because substitution is dependent on the fact that you need to have the characters be equal at the index you're looking at in order to do the substitution operation. So this is like a glossing over a little bit of the details, at least to me. So here it's fine. And then so he's still running through the idea. I get that this is mostly because he is unfamiliar with it. And so I'm actually okay with him testing for like 10 minutes actually. But it just says that he's weak at the at dynamic programming. And then he also realizes that at the end that he needs to have this condition here. But this is like an observation that you can actually I don't even think this should be 0, because the reason why is that if I plus 1 I2 at the end then return, that's the problem with going like from right to left. It just like makes it super confusing. So I mean, like, this should have been immediately obvious. And he could have easily said that as well. But then where he actually ends up, and I want to skip to the end here, is that he's actually crystallizing his ideas here with the pseudocode. And then if we jump forward, you can realize that his code is actually wrong here. And the reason why is because, well, I want to compare it to like the solution that the book provides. Let me show you the code here. This code here actually matches the pseudocode that he's doing. So let me actually bust open the book and let me show you guys the actual solution here. So 306. Cool. So let's go through so here's the book solution, here's his solution. Let's kind of go through this step by step. So overall, like, this is just initializing if the problem has been solved for or not. And here is just saying if all of B's indexes are empty, then add all of A's. If otherwise, add all of A's, you know. And this is really what he's trying to do here. But really, it's, you know, it's just this, you know. So it's fine. So I don't have a problem with, like, setting it up here, because, you know, the book actually kind of does a recursive solution here. So then here is where the real meat of the issue comes in. So that if the distance hasn't been solved for, if the characters are the same, then you do the computation of substitution. Otherwise, you use the addition or deletion. So this is where it kind of gets a little bit messy, I think. Yeah, so substitute last, add last, or delete last. Yeah. I mean, in theory, yeah. So basically, this is kind of like where he messes up. Is that he's using the minimum of add or delete, But then he also needs to realize that if they're the same, then you need to use the substitution. But yeah, basically the bottom line is that he kind of just assumed one case when he could have actually had a better computation if he had this. So let me explain. So for instance, is there a situation where this is actually usable? Like why do we need to even have this? Shouldn't this take care of it by itself? Well, not necessarily, because let's say that you end up in a situation where you have, you have some level of string, right? And then you have an A here, right? And so for this particular string, you can either have, this substitution, this level of string, whatever it is, and A. But then what happens if your second string is also A? Well, then based on what we saw here, then you end up with this substitution. But then the substitution may not necessarily be needed. So that's kind of the problem here. So it's when the strings are equal that you actually end up being forced, that substitution will always be optimal. That's it. So I would say to try and look at that particular situation to begin with. So other than that, I think he did pretty well. He got really close though. But yeah, I guess with that, I'll take questions from the crowd. If there's no more questions from the crowd, then I guess I'll stop the stream for today. Yeah, thanks for watching, guys. I will be streaming again Monday, Tuesday, Thursday, Fridays, 8 p.m. to 10 p.m. on Monday, Tuesdays, 9 p.m. to 10 p.m. on Thursday, Fridays. So hopefully you guys will join me again for that and watch these guys make progress. So with that, have a good night.